Welcome to part 2 of Stoke's theorem. In this video we'll use a line integral to evaluate a surface integral based upon Stoke's theorem. In part 1 we did the opposite. We evaluated a line integral using a surface integral. So as a quick review, here's Stoke's theorem, and it states the relationship between line integrals and surface integrals of a vector field under specific conditions. And it tells us that the net rotation over the surface is equal to the net rotation along the boundary C. Given that all of the following conditions here are met. And since we discussed all of this in part 1, we're going to go ahead and go straight to our second example. In this example, we want to use Stoke's theorem to evaluate the surface integral of the curl of f dotted with n integrated with respects to s. And we have the given vector field, and our surface is given by z equals 4 minus x squared minus y squared above z equals 0. So let's go and take a look at this graphically first. So our surface is this blue surface above the yellow plane. So our curve C would be the circle in the xy plane. Remember, based upon Stoke's theorem, we're going to assume the orientation is counterclockwise and the surface has a positive orientation. And so when we determine this surface integral, it's going to tell us the net rotation on the surface from this purple vector field. It's also going to equal the net rotation along the curve C in the xy plane. Looking at this vector field, you can see that it looks like it will be clockwise based upon this vector field, so we should get a negative value since it is in the opposite direction of our orientation. Let's go ahead and set this up. So again, now instead of evaluating a surface integral, we're going to evaluate a line integral along the boundary C. So our first step will be to parameterize our curve for the line integral in terms of t. Well, our curve will be the xy trace of our surface. So if we set z equal to 0, we would have x squared plus y squared equals 4. So we have a circle of radius 2. So r of t is going to be equal to 2 cosine t, 2 sine t, 0. And we'll also need the derivative. So we'll have negative 2 sine t, 2 cosine t, and 0. And we should also recognize by now that if this is our curve, we know that t will be on the closed interval from 0 to 2 pi. I think we have everything that we need. Let's see if we can set up this integral in terms of t. The limit of integration will be from 0 to 2 pi. We need to rewrite our vector field in terms of t using our parameterization. So we have x equals 2 cosine t, y equals 2 sine t, and z would be equal to 0. So our vector field is z, comma, negative 2x, comma, x times y. Well, z is 0. Negative 2x will be negative 4 cosine t. And x times y is going to be 4 cosine t sine t. And we're going to dot this with r prime of t, which we found here in green. Let's go and determine our dot product. We're going to have 0, then we'll have minus 8 cosine squared t, and then 0. Let's go ahead and evaluate this on the next page. Let's go ahead and apply a power reducing formula here for cosine squared t. So we'll have negative 8, 1 plus cosine 2t divided by 2. So we're going to have negative 4, 1 plus cosine 2t. Here we'd have a u substitution. So in converting to u, we have an extra factor of 1/2. So we'll have t plus 1/2 sine 2t so when t is 2 pi, we'll have 2 pi plus sine of 4 pi is going to be 0 minus 0 plus 0. So it looks like we have negative 8 pi. So this tells us that a net rotation would be opposite of the orientation. So in this case, it looks like it should be clockwise. Let's go ahead and look. Now it's not easy to tell, but it does look like the way this vector field is oriented, the net rotation would be clockwise in this direction. And therefore, as you can see, we had a negative value. And that's going to do it for Stoke's theorem. Thank you for watching.